Um, if you have a USB-C to C, then you can use this, or like E to C. Otherwise, no. If I disconnect some of these, I'm not confident in what will happen. Hmm, there. Oh, that's cool. Oh, hello. Good. How's it going? Good, good, good. Hello. Okay. So, wow, there's so many of you. How nice. Hello everyone. Welcome back to Comfrey 30. As you might have already noticed, uh, Jérôme is not here. I'm not Jérôme. So instead, I'm Cesare. That's how you pronounce my name in Italian, and that's how you write it in English and in Italian. However, I'm fine with this pronunciation, Ches, and then array. So, feel free to call me Cesare. Feel free also to call me Ches. It might be a little bit weird if you call me Array, so maybe don't do that. So I'll be giving today's lecture because Jérôme is traveling to Quebec City. Lucky for him. But I'm happy to be here. And so before we get started with the material for today, which is going to be about regular expressions, I just want to give you two quick announcements. I was going to do one, but now I realize maybe I should do two. So the first announcement, which I already sort of posted on Ed, is that tutorial 2 is canceled, which I'm sure many of you are disappointed about. So sorry to disappoint. Instead, because the tutorials I still think are useful to sort of give you solutions to the problem sets, I've posted videos instead. So there's posted videos for some solutions, I guess, with solutions. The second announcement was, I think, so someone raised a good question on Ed, which was asked again just now. The midterm 1 date has been slightly pushed. So instead of being I forget when it was supposed to be. It's going to be the 30th of September. Okay, so hopefully that's better and not, oh, that looks like it's worse, but hopefully it's not that bad. Okay, so yeah, so those are the two announcements. Any questions about admin before I get started? Yes? The date of midterm 2, the best information I have is on this piece of paper. The information that I have for midterm 2 is that it should be on the 28th of October. So I'm not sure if that's different, but yeah. Okay. Yes? Is the content of midterm 1 going to change? I mean, was the content of midterm 1 announced? Okay. So then I guess yeah, but this is a good question. But yeah, so the content is going to be up until what we cover. We're already starting to think about what the midterm should look like. So maybe before we start, I'll give you a small analogy of about last year's midterm. So last year, I was also TA for Jérôme. And yeah, the midterm was maybe a bit too long. I don't know if anyone heard about this. So we had asked like several follow step by step this algorithm procedure in the midterms. There was like 2 or 3 questions about that, and yeah, I wasn't a fan of those questions. And it ended up being that those were the questions that took up the most time. So this year we're not going to make that mistake. We're not going to ask any like follow step by step this algorithm that we presented in class in the midterm. So you can hopefully that's good news, right? So it's going to be more conceptual level questions. Okay, good. Everyone's happy. I see one smile, so that means everyone's happy. Okay, good. So the topic for today is going to be about regular expressions. So what are regular expressions? For me to talk about what regular expressions are, I think a nice way to start is to talk about what you've seen so far in Complete 30, right? So what have you seen so far in Complete 30? I mean, you've had a few lectures. You've seen stuff on like DFAs. You've also seen stuff on NFAs. And you've also seen stuff on NFAs with epsilon transitions, right? So all these things, right? All these things are what I would call theoretical models of computation. Right. And I mean, that's great, given that the title of the class is Theory of Computation. It's great that what we've been studying so far are theoretical models of computation, right? And so in the most concrete way, how have these been like theoretical models of computation, of algorithms, of procedures? In the most concrete way, you can just think of them as sort of providing the steps, right? So when you think of a DFA, when you think of any kind of FA, right, you can essentially think about it as some sort of procedure that gives you the steps for accepting some set of strings. Some set of strings. Right, if you look at an FA and you look at its transition diagram, the transition diagram, its states and its edges are essentially like the instructions that you're supposed to follow if you want to accept certain strings, right? So that's in the most concrete way, in the most like tangible way, hopefully, that's how it kind of resembles the algorithms that you've been taught so far in CS at McGill. So that's great, right? Hopefully it's been interesting so far. There's a bit of a limitation though. So there's a bit of a limitation to this perspective of computation. And the limitation is that FAs as such are not a compact, description of the strings accepted. Okay, so what do I mean by this? So a good analogy, which I think will help to make this limitation more concrete. So I'm sure you've taken like some CS classes where in a midterm or an assignment or whatever, you're given some piece of code and then you're asked, as the question, what does this piece of code do? Right? Like hopefully that's been a question that's been asked to you. If you only have this like FA mindset, then how would you answer this question? Well, you would say, okay, what does this function do? What does this algorithm do? Okay, on step 1, there's a print statement. On step 2, there's a variable assignment. On step 3, there's an if statement. On step 4, you open the body of the if statement, right? So you can kind of see that this is not really a description of what the function does, right? It's just sort of the steps taken by the function. So what would be nice is if we had some kind of representation of what a function, what an algorithm, what an FA does. And so that's exactly why today we'll be talking about regular expressions, because regular expressions are kind of like the flip side of FA, where you don't really need to follow the instructions. You just really have to specify what you're supposed to be accepting. Okay, so that's going to be the idea of regular expressions. And so as a definition for regular expressions, I'm going to give you an informal definition first, and then we'll see a more rigorous definition later on. So a regular expression is a mathematical object, of course. Mathematical object which explicitly describes the pattern or the patterns followed by strings in a language L, which is a subset of sigma star, where, you know, sigma is just for the sake of simplicity, not empty, right? So there's something in sigma. Okay, so this is my informal definition. If there are any people taking math, then you'll be very unsatisfied by this definition, and I understand. But let's start with an informal definition, and then let's get to the formal one a bit later. Okay, so far, what I've been talking about has been very abstract. And so I think the best way to make something that has been discussed so far abstractly not abstract is by looking at an example. I could have phrased that a bit more clear, but okay, let's look at an example of a regular expression and of what I mean by sort of describing the patterns in a language. Okay, so suppose my alphabet is 0, 1, right? So the strings over this alphabet are sequences of zeros and ones, right? And now consider the following. Consider the following. Following regular expression R. So I'm going to use the variable R for regular expression. Hopefully you can see why. 0 plus 1 whole star 0, 1. Okay. So this is the first, this for some of you might be the very first regular expression you've ever seen in your life. If that's the case, I'm very happy to be part of this moment. If you've already seen some regular expressions, then hopefully this one's different from the ones that you've already seen. Okay, so this is a mathematical object which I claim is supposed to be somehow explicitly describing the patterns in some language. Okay, so what is the pattern being described here? Well, let's, to answer that question, study the regular expression piece by piece. So let's first start with sort of this piece of the regular expression. So let's look at the 0 plus 1 thing. So the 0 plus 1 thing, if I just abstract it for a small second, this is kind of if you have, this is sort of following the rule of if you have one regular expression plus another. Okay. And so the logic of regular expression syntax, when you have regular expression 1 plus regular expression 2, is that this is describing patterns which strings which either match the pattern described here or here, right? So in this case, what is the pattern? Well, it's either the string is 0 or the string is 1, right? So the strings here, so strings which match with 0 plus 1, which I'll typically, or I'll start to say 0 or 1, either have a 0 or a 1. And actually, more precisely, they're either 0 or 1 exactly, right? So this is what 0 plus 1 is. And in general, if you have regular expression 1 plus regular expression 2, what is the pattern being described? The pattern being described is that strings which match this pattern either have one of these two patterns. That's essentially what it's doing. So it's a bit of a recursive definition. Okay, so that's 0 plus 1, right? Now what happens if I wrap the 0 plus 1 around the star? Or I use a star to wrap the 0 plus 1. So 0 plus 1 star. So this is another very classic sort of syntax in regular expressions. And what it means when you have something like regular expression whole star, this is saying that strings match with this pattern if they have this pattern 0 or more times, right? So that's what the syntax here means. So in this case, that means that strings which match with the 0 plus 1 star contain 0 or 1, right? Any number of times in a row. So any number of times in a row. Okay, so that's the pattern described by 0 plus 1 star. So now if I take a small break and I don't go all the way to this regular expression yet, and I sort of introduce an extra piece of notation, the language described by the regular expression 0 plus 1, right? So this is the notation. It's L of regular expression. So L of regular expression is the strings in sigma star such that W matches or is described by R. Okay, so that's what the syntax means. So yeah, give me a second. So give me a second. So what is L of 0 plus 1? So it's strings that contain exactly 0 or exactly 1. Or in other words, it's exactly the strings that are 0 or 1. So the language described by this pattern 0 plus 1 is 0, comma 1. Okay. So then if we're using this kind of intuitive description that I've been giving so far, then what would be L of 0 plus 1 whole star? Question for you. Maybe tricky. So remember, 0 plus 1 star describes any string that has any number of zeros or ones in a row. Okay, let's think of strings over the alphabet 0 or 1. Well, strings over the alphabet 0 or 1, they have zeros, and then they have ones, and then have zeros, and then they have ones. Oh, okay, so it sounds like 0 plus 1 star describes the entire sigma star, right? So that's what is described here. Okay, so this is just an interlude, just so that we get a bit more familiar with the notation. Now, if we go back to the last thing, right, the last part of the regular expression, let's just move this slightly down. If we get something, or if we have something like 0 plus 1 whole star 0, 1, then this is another, and this is actually the final sort of piece of syntax that you're going to see in regular expressions, which is essentially when you have something like regular expression 1 followed by regular expression 2. So when you have something like that, it means that for strings to match, or for strings to be described by something like this, or in more general something like this, then their first part has to sort of match with this pattern, and then their second part has to match with this pattern, right? So then if I just write this sort of intuitively, 0 plus 1 star 0, 1, what are the strings which match with this regular expression? So strings match with 0 plus 1 whole star 0, 1 if they start, right? So they start with the first pattern here, so this first pattern here. So they start with any number of zeros or ones in a row, right? And then, right, and then if they start and then are followed and then are followed by this pattern, right? They're followed by strings that match this pattern. So in this case, the only string that really matches this pattern is the string 0, 1, right? That's the pattern described here. It's kind of like hard-coded. So then are followed by 0, 1. Okay. So then, give me a second. So then if I return to my notation here, L of 0 plus 1 star, 0, 1, then let's see, what are the strings that are described by 0 plus 1 star 0, 1? Well, okay, now these are strings that start with zeros and ones, zeros and ones, zeros and ones, so any string, and then are followed by 0, 1 and only 0, 1. Okay, so really in natural language, that's like any string that ends in 0, 1, right? So W in 0, 1 star, such that W ends in 0, 1. Okay. And before I take questions, I just want to sort of emphasize the point that I was making at the beginning. So regular expressions describe the patterns, describe the strings that are supposed to be accepted, right? So you can kind of see this, right? You have this nice compact representation of the strings in the language versus, if I wanted to make an FA that represented this language, then I would need to do something like, I don't know, if I made an NFA, then I would have to do something like I have a self loop with 0, 1, and then at some point I have to have 0, 1 to accept. So then at some point I have to have 0 and then 1 and go to accept state, right? So the point I was trying to make is between this as the description of this language and this as the description of this language, this one, at least to me, is much more natural, right? So we're like explicitly describing what the strings in the language should be, and we don't just have this sort of mechanism or this procedure for accepting the strings. Okay, so now at this point, I can take questions. Yeah, there were more questions, but maybe, hopefully I answered them. That's what that means. Yeah. If they start, oh, sorry. If they start with, okay, yes. Good point, yes. I've been told to work on my handwriting. I've yet to find the time. Yeah?
I was going to ask, does the string specifically use the word that are followed by 0, 1? Does it
Yeah.
end, or is it okay if something?
Okay, good question. Yes. So the question is, can there be something after the 0, 1? Yeah, so no. It has to really end with 0, 1, right? Because if you have some string like 0, 1, 1, 0, 1, 1, 0, right? Then for this to match with this guy, right? Then I need to somehow have this guy overlap with the end of the string, and then I can explain the rest of the string with the 0, 1 star. So here I don't have 0, 1 at the end. So the only thing that my sort of pattern can try to explain is the fact that maybe this is like for 0, 1 star, and it's kind of waiting for the extra 0, 1 to be there. Otherwise, it's not going to match. Yeah.
That's not just a consequence of the fact that we have 2 letters. That's also true in general. Like even if you were to make like a regular expression out of the Latin alphabet or whatever.
You mean if you just had like a string here?
I guess because my point is the first part, like the 0 plus 1 star, that's like the whole alphabet.
Yeah. It's any string. Yeah. Any string. Yeah.
So, I mean, in a case where that's not true, like if you were to use like alphabet, you put A plus B star, like C at the end. Because like there are more letters in that case than just A, B, and C.
Yes. Okay, I see. Yeah, so then in that case, right. Okay, so I think that's a nice question. The question here was, if you have the alphabet, say AB.
Well, I was just going to say like A, B, C, because in this case,
ABC.
letters, right? So the first part, you can say that anything is the first part.
Yeah. So if you have R is like something like A plus B plus C star C, right? And then you're like, oh, will this match with hello C, right? Something like this. Well, no, because this string is not well defined under this alphabet. That's the kind of cheap answer here. So really what you need is you need the alphabet to have all the symbols in the string. Otherwise, this is kind of like if you had a keyboard with ABC and I said, okay, I'm going to type hello, and it's like, where's the key for H and E and L and O? Yeah.
That's not exact. I'll just ask you.
Okay, okay. I think I know where you're getting at, but yeah, it's a good, nice, deep question. Any other? Let's go you and then you.
I was wondering if the diagram, if it
Yeah, that one. Yes. Yes. Yes.
how do you know?
Aha. Well, this is an NFA, right? This is an NFA. Yes, good. So there was a question here like, well, I have a 0 here and a 0 here. So how do I know which one to take? Well, I use non-determinism, right? I guess that at some point I'm supposed to transition and use this one. Right. Okay. Excellent. Very good. So this is, it's good. I didn't point it out. This is an NFA. Okay. Any, oh yeah, sorry. I forgot. Sorry.
In this case, would 0, 1 count affected?
Ah, that's another good, I was expecting that question. So another very good question. Another very good question. Is 0, 1 described by 0, 1 star 0, 1, right? Okay, I'm gonna do the classic like pedagogy thing and be like, oh, what do you guys think? What do you guys think? Yes. Why do you say yes?
Because I thought that like the empty
String,
empty
yeah.
word is part of every language.
Yeah. Very good. Yeah. So you're hinting at the empty string. Excellent. So, 0, 1, 0, 1 is the same as the empty string 0, 1, right? So, and remember, what does 0, 1 star match? It matches any number of zeros and ones in a row, any number of times, including 0, right? So the empty string is zeros and ones in a row any number of times, namely 0 times, right? So you have 0 times here, and then you have 0, 1 here. Yes, good question. Okay, very good. Excellent. Any other questions? No, okay. You want to hear something cool? I wrote 3 p.m. and it's 3 p.m. I can see the future. Okay, all right, let's look at another example. So in this case, I'm going to change the alphabet. It's going to be AB. But again, I'm going to do the sort of similar exercise, and I'm going to ask, what is the language? What is the language described by the following regular expression R? Where R here is going to be A plus B star, ABA, A plus B star. Right, so now, a similar question. I'm not going to go as slow as before. I kind of want to know, well, what are the strings that are described by this pattern here? So let's think of like an arbitrary string X, right? So suppose X is in sigma star, where, sigma is AB here. Then what does X have to have for it to match with A plus B star, ABA, A plus B star? Well, it has to start with, any number of A's or B's in a row, any number of times. So any number of A's and B's in a row. So any number including 0. Then it must have the string ABA, right? It must have the string ABA because it's encoded there, right? I've like hard-coded ABA in my pattern. So then the string ABA, right? And then again, any number. So then again here, it has to have any number of A's and B's in a row. Okay, so that means that the strings that are described by this regular expression are any number of A's and B's, any number of A's and B's, ABA, and then any number of A's and B's, any number of A's and B's. Well, that sounds like the string, for it to be described by the regular expression, it has to have ABA as a substring, right? And the string is only described by the regular expression if it has ABA as a substring, right? So hopefully that's convincing. Are we convinced? Yes. Nods? Good. So the language described by the regular expression R is strings of the alphabet AB such that W contains the substring ABA, right? And this is actually a language that's that we have written up in the problem set 1 as like a design a DFA for this language. So you can also find this language in problem set 1, and you can sort of compare the regular expression and the FAs and DFAs, and again get the point that the FAs are much more clunky when it comes to describing this language, and I would say the regular expressions are much more, this is nice and elegant, nice compact way of talking about a language. In general, what we've been looking at so far, really, the idea that I've sort of am trying to convey is if you have the space of regular expressions, right? So you imagine all the possible regular expressions in the world that you can think of. Then what these regular expressions are doing is they're like these compact representations that point directly to a language, right? So if this is a regular expression and this is the space of languages, I'm not going to tell you what type of languages just yet, but maybe you can guess. Then, this regular expression R1 goes to L1, this regular expression R3, well, let's be a bit more specific. Goes to L of R1, this goes to L of R3, and so on, right? So what I think is kind of cool is, you have a regular expression. It's sort of this object that is finite, right? It's clearly finite. There's, 10 or something objects, like atomic objects in here. But what it's doing is that it's pointing at an infinite thing, right? So you're sort of doing infinite compression, right? You have an infinite language and you're able to compress it to a finite object. So I think that's pretty cool. I saw one person nod. So that means that at least one other person thinks it's cool. Good. Okay. Questions about this example? Feel like, no? Okay. Yeah. Okay. Oh, this thing? Oh. W contains the substring ABA. Oh, this is just problem set 1. Yeah. Oh, sorry. It's again a question about writing. Maybe I should really work on it. Okay. Any other questions? No. Okay. Yeah. Oh, yeah.
Slightly not like, okay, so for the problem set, like if we have a limited amount of time and couldn't do all of it, like do you recommend we do every question one after the other? Like
I see. This is not exactly relevant to this example, but I think it's been on people's minds. So the question was, do you have to do every single question in the problem sets? Right? That's the question. How to answer the question? Before the midterms, so before both of the midterms and the final, I will be much more explicit as to what would be good to practice further. Yeah. So don't worry about it too much. Yeah. But I think there are some questions in the problem set that like would never be in the midterm, but that are kind of cool. Like question 11, for instance. I think it's kind of cool. But, good question. Any other questions? Yeah. Ooh, very nice question. Ooh, I like that question. Nice. Can two So there's a question here, very nice. Can two different regular expressions describe the same language? Right? That's the question. Okay, I'm going to do the classic thing. What do you think? Yeah, you think so? Yeah, I think I agree with you. Because for instance, maybe I'm going to give the example now because otherwise it becomes a bit stressful in my opinion. So, you have R1 is maybe A plus B whole star, right? So this describes AB star, right? So all the possible strings. But now I could just as easily write something like this. A plus B star, and then A plus B star, right? It's kind of cheap, but yeah, this definitely also describes L of R2 is equal to L of R1. So yes, definitely, it can do that.
And is it the same effect B plus A star or is that different?
Yeah, B plus A star is the same. So A plus B star is the same as B plus A star. But, so this is a question for you, because, you know, I love taking questions, but at some point, I maybe have to move on. Is a question for you, is it true that given two regular expressions, so given regular expressions R1 and R2 are R1 plus R2 star equivalent to R1 star plus R2 star. So here equivalency means that the languages they describe are the same. Okay, so I recommend you look at this question because it's a pretty good midterm question. Hint, hint, nudge, nudge. Okay, so let's do one final example. And then let's do, then we'll make the mathematicians in the room happy and give formal definitions. So let's look at the alphabet 0, 1. Okay, and now I'm going to do the flip. So I'm going to say, now I'm going to give myself and you and everyone here the language and say, okay, let's find a regular expression for it. So create a regular expression such that the language, regular expression R, such that the language described by R is strings, of course, over 0, 1, such that W has an odd number of ones. Right, so for instance, something like 0, 1, 1, 1, that should be an L of R, but W 2, 1, 0, 1, that's not going to be an L of R. Right, so now the goal is kind of opposite, right? It's like, I have a language and I want to describe a regular expression that talks about the pattern in the language. Okay, so how am I going to do this? The general strategy here, so the general strategy that I recommend is first sort of find the pattern, right? So find the pattern or patterns in L of R, and then try to convert it, and then convert it to regular expression syntax. Okay, this is my recommended way of doing these types of questions. So how does, what does that look like? Suppose I have a string W, which is supposed to be an L of R, right? So what is the string W, what is it supposed to look like, right? Well, it's supposed to have an odd number of ones. So, if I have my string W, then, maybe it's super long string and it has an odd number of ones. So it has ones here, 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 maybe some more here, and then one last one here, okay? So the pattern that you might notice once you stare at this a bit long enough is if my string has an odd number of ones, then I'm going to have pairs of ones, right? Pairs of ones, right? I'm going to have pairs of ones and then one dangling one, right? So that's the general pattern I'm going to have. So the general pattern that appears is I have pairs of ones. So pairs of ones followed by a single dangling one, right? And you can also just get this from the fact that, odd numbers look like 2n plus 1, right? So there's pairs, then you have an extra one, right? You can also, if you also saw the pattern of, oh, I have one dangling one at the front and then pairs of ones, it would work the same. You could say, oh, I have a dangling, well, yeah, it would work the same. I'm not going to get into the other possibilities. Okay, so that's great, right? But my alphabet is 0, 1. Did I say that my alphabet was 0, 1? Yes, right? My alphabet is 0, 1. So zeros are likely, between the ones, before the ones, after the ones. So that means that for the pairs of ones, right? For the pairs of ones, I can have any number of zeros before the first 1 in the pair, any number of zeros between the two pairs of ones, or between the pair of ones, and then any number of zeros after the second one in the pair. So, I have any number of zeros here, zeros here, and here, and here, right? And then at the very end, right? And so this pattern, of course, with the zeros repeats, like the same logic applies also to this guy and to this guy. I can have any number of zeros here, any number of zeros in between, right? And so on. Right. And then for the last dangling one, it's also super fair game if I have, zeros before and zeros after, right? And that, I think, in general, is the pattern. Okay, so it looks like I actually have a pattern within a pattern, right? So I have this guy, and this can happen any number of times. And then this guy has to happen exactly once, right? So then what I can write first is, let's write the pattern, within. So I have 0 star, because 0 any number of times. The first one, 0 star, because 0 any number of times. And then the second one, and then 0 star. And then this can repeat, right, any number of times. So I have a star around this. And then after, I need my dangling one, which can be preceded and followed by any number of zeros. So then I have my dangling one, and then I have zeros before, and I have zeros after, right? And this is a regular expression, R, which satisfies the conditions in the language. There are other regular expressions that you might have thought of, and that's also super cool. For instance, an exercise for you, I'll get to you in a second. So an exercise for you is, given the R that we just wrote, is the following alternative regular expression R prime equivalent to R. So this alternative regular expression is going to be very similar, right? Except that it's not going to have this 0 star here. It's going to have just 1 and then 0 star. So the question here is it okay to omit this 0 star? So that's the question that I'm going to leave for you, which would also be a nice question in a midterm. That was your question. See, I can see the future. Yeah, nice. Okay, yeah? Oh, yes, thank you very much. Amazing. Nice, thanks. Any questions about this? Yes.
Could you also omit the 0 from within the parentheses in the back of R?
I'm not sure. I can also write that one. So what about, which one is it?
So instead of removing the 0 just out of the parentheses, the one just before the close parentheses.
So what about?
Yeah.
Let's do 1 0 star.
Or no, 0.
Oh, with the 0 star. Yeah. Yeah, nice question. Nice question. I'll leave it for you. Nice question. Okay. Any other questions? These are really good questions, guys. Keep them up. I like this. Yeah. Yeah, nice. So the question is, can it not end with another pair of ones? So yes, right? I mean, yeah, there could totally be an extra pair of ones here. But then what would actually happen is your pattern would pick that up because it would say this one and this one is a pair. And then you get that dangling one here. Yeah. Nice question. Okay. Nice. All right. Okay, so unfortunately, this is the last example. Well, is it? Okay, there isn't another example in a while. So sorry. Now we have to do some real maths. Okay, so let me give a definition. So I'm going to give what I will call a formal definition of regular expressions, and which other math profs would call still an informal definition. So the definition of regular expressions, this definition is due to Stephen Claney, who sort of proposed this definition in 1951. And a fun fact about Stephen Kleene is that he was sort of known to have a very, very loud voice. So whenever he would have office hours, if there was another sort of office open at the other side of the hall, then you could hear him sort of talking to the students. And he was explaining, like, he was nice, but it was as if he was yelling at them. So it's kind of intense. Imagine. All right. So suppose we have an alphabet which is not empty. Then I'm going to define what a valid regular expression looks like. So a valid regular expression consists of atomic regular expressions joined together with regular expression operators. Okay, so I mean, to make this even more formal and make the most rigorous of mathematicians happy, then you would have to sort of define this a bit more recursively. I'm not going to do that because this definition is already pretty unambiguous in my humble opinion. So there's like two key words here, or two key phrases. There is atomic regular expressions and then regular expression operators. So essentially, this is like a recursive definition where it's like you have your atomic regular expressions and you build up more and more complicated regular expressions using the regular expression operators, right? And then at the end, you sort of get the regular expression that you kind of care about. Okay, I'm going to answer your question at the end of my definition. Okay. So first of all, what are the atomic regular expressions? So the atomic regular expressions are the following. So I have the regular expression. So I have the regular expression which denotes the empty set, which looks like the empty set, but all of these guys are going to be of type regular expression. Okay. Then I'm going to have the regular expression, which looks like the empty string, but actually is a regular expression and denotes the empty string. And then I'm going to have the regular expression that looks like a letter for every single letter in the alphabet, but really it's still of type regular expression. Okay? So this is just small subtle point. And so you can think of this as kind of like the base case of your recursion. So it's kind of like the base case of the recursive definition. Okay. And then what are the regular expression operators? Well, actually, we've already seen all the regular expression operators. So the regular expression operators are the following. So what they do, just to remind you, what they do is given a valid regular expression, or given, I mean, there's two actually. So given valid regular expressions, R1 and R2, the regular expression operators, I'll use the wording build up, more complex regular expressions, and the more complex regular expressions are R1 plus R2, R1 dot R2, R1 star, and then just for good measure, we have to define brackets so things can sort of be disambiguated when you do order precedence. So essentially, you can think of this as kind of like the recursive case. This is like the recursive case of your definition. Okay, and the logic of each of these things I've sort of already presented intuitively. Now to actually see how they're truly implemented, I have to define formally what the language described by a regular expression R is. So before I get to your question, if you still have one, let me just give an example. So what's an example of a valid versus not a valid regular expression. So valid versus not valid regular expression. Okay, so suppose the alphabet is AB, then the following is a valid regular expression. So let's do A plus B plus epsilon dot B dot A plus empty set star, right? So this is valid. This is a valid regular expression. It's valid because all of the sort of pieces, right? This A, B, this epsilon, this B, this A, this empty set, these are like the atomic regular expressions. And then we build up a more complicated regular expressions using these operators. So we have my dot, the dot here and here, the plus here and here, the brackets, and then the star here, right? So I'm just building things up from the atomic regular expressions. And then here's an example of a regular expression which is not valid. So something like A intersect B, different, B reverse, empty set, right? So this is not valid. This is not a valid regular expression for several reasons. So firstly, I use these set theory operators, which I'm not allowed to use in regular expressions because they apply to sets, not regular expressions. And then the other thing, which is kind of like a subtle point, is this is the empty set, right? So this is the empty set. The empty set is of type set, right? So if you're taking 302, hopefully you know what I mean by types. So the empty set is of type set, whereas this thing is the regular expression. So this is the empty set regular expression, which is of type regular expression. Okay, so there's an unfortunate overloading of notation, but you know, it wouldn't be a CS class if you didn't overload notation. Okay, yes, question.
So it seems intuitive to me that the language of regular expressions is itself not regular.
Ooh, wow, that's a really good question. The language containing all of the regular languages, right?
Oh, the regular expression, but specifically this notation, the language of this.
Huh. Yes, nice question. So this is kind of an advanced question. Just for you, I will tell you. So it turns out that the language of regular expressions is context-free. So you kind of need a context-free grammar to generate all possible regular expressions because you kind of have to handle brackets and things like that. So yes, that's a nice point. Yeah. I won't write it down because it's a bit of a, but actually it might be in a problem set. Yeah. So yeah, nice question. Yes. Oh, yeah. So it's normal that you're confused. If when I get to L of regular expression, then it's going to be super clear what it means. But like I'll tell you right now, L of the empty set, like the language denoted by the regular expression, that's the empty set, is the empty set. And the language that's denoted by the epsilon is the language that contains the empty string. So those are different. But yeah, I'm going to define that just now. But yeah, good question. Yeah. Go up. How up? More. I'm going to post this. Okay. Yeah? Two things. Okay. Let's do one by one because I don't know how other people, so much cognitive load. Yeah. First thing.
So isn't epsilon the alphabet? Which all the singular symbols that you
Uh,
what is that?
oh, this. Oh, this is this, right?
No, I mean sigma.
Sigma?
Yeah.
Oh, this is just the alphabet. So this is like, for instance, here, if I had written the regular expression A plus B plus C, then even though I'm using only atomic regular expressions and only regular expression operators, C is not in the alphabet, so then it's not a valid regular expression. Yeah? Yeah, okay.
And also,
Yeah, oh yeah, second, yeah.
the dot operator is
Yeah, so this is the dot, operator for regular expressions, but we'll see in a second that it directly transfers to the language concatenation. So yes, basically yes. Okay, nice. Good. Thank you for both questions. Okay. Any other? Yes. Yes, yes, yes. L of empty set star. It'll be clearer when I derive it later. But yes, yes. That's a good like prediction of what's to come. Okay, nice. But good question. Any other good questions? No? Okay. Okay. All right. So this is how you sort of define valid regular expressions. Now, how do you define the languages denoted by regular expressions, which are, of course, valid? So the question that we're now faced, well, first of all, what time is it? 3:28. Okay. Oh, nice. 3:30. Wow. Okay. Right, the question we're faced is, in addition to what time is it, is given a regular expression, how do we determine L of R, right? So that's the next question that we have to ask, right? So, I mean, it's all nice and good to define valid regular expressions, but they're not that useful if you can't do L of that, right? Because then it's meaningless, right? They're just symbols. So again, the answer is going to be via a recursive procedure. So we're going to sort of define the base cases, which is what is L of R, where R is an atomic regular expression. And then we're going to define what L of, R1 plus R2 and all of the other regular expressions operators give in terms of languages. So let's do the sort of base cases first. So the base cases are languages which are described by the atomic regular expressions, right? So the languages described by the atomic regular expressions. Well, what are the atomic regular expressions? Well, there's the thing that looks like the empty set, the thing that looks like epsilon, and then A for any letter A. So what happens when you do L of this? Well, unsurprisingly, you get the empty language, so the language that contains no strings. When you do L of this, then you get, you don't get the empty language, you get the language which only contains the empty string, right, which is different, right? So these are not the same, right? Not the same, namely because the size of L of empty set is 0 and the size of L of epsilon is 1, right? So of course they can't be the same, right? And then finally, what about L of A, where A is a regular expression that denotes a letter? Well, that's just a language that contains only that letter, right? So hopefully that makes sense. Okay, so then how do we do the recursive cases? So to do the recursive cases, essentially, so we've defined like what happens when you get L of any of the atomic regular expressions, but then how do you actually get there, right? Because what you're going to do is you're going to try to like break L of this into smaller and smaller parts such that you only have like L of A and then L of B and so on. So how do you actually do this breaking up? Well, you need to use the recursive cases where essentially we map regular expression operators to language operators. To language operators. So for instance, if I have R1 and R2 as valid regular expressions, then L of R1 or R2, well, what does L, well, like what should L of R1 plus R2 equal if I've been talking about the plus as disjunction? Anyone? Well, the disjunction or the inclusive or is like a union, right? So the plus just becomes a union for languages. So we get L of R1 union L of R2. Okay, so I'm just taking this regular expression operator and I'm mapping it to an operator over languages, right? Because ultimately that's what I care about. I care about the languages that are described by the regular expressions. Otherwise, they're just symbols that are on a piece of paper or an iPad. Okay, so what about L of R1 dot R2? Well, this dot, so this dot for the regular expressions becomes the concatenation for languages, right? So I get L of R1 and then L of R2, and I combine them together by concatenating with a dot. Okay. And then the last thing is what is L of R1 star? So L of R1 star, that becomes, you know, the star of L of R1, where the star is sort of the Kleene star operator on languages, which if you watch one of the tutorial videos, I define. So there's extra motivation to watch me talk about languages. Okay. And this essentially sort of completes all of the recursive cases. I mean, I guess I'm missing this one, but you know, L of bracket R1, that's just L of R1. Okay, so I mean, hopefully that's not too surprising. So I just remove the bracket. The last thing before I get to a more concrete example is, you know, what is the order of precedence? For regular expression operators. Okay, so the order of precedence, essentially like, what do I favor over what when it comes to operators and converting them to the language operators? So the order of precedence is essentially the bracket is the most important thing, then it's the star, then it's the dot, and then it's the plus. So concretely, what this means is that if I have A star dot B plus A, then there's like multiple interpretations of this. There's either the interpretation of, oh, this means that it's A star dot B plus A. But there's also the alternative interpretation of, oh, this is A star dot B and then plus A. So based on the order of precedence, you know, the dot is before the plus. And so that means that this one is incorrect and this one is correct, right? Okay, so that's just in case you were wondering. Okay. So far, so good? Yeah. Ooh, very nice question. The question was, are there languages which regular expressions cannot describe? Okay, so that's a very good question. So, spoiler alert, the reason why they're called regular expressions is because they can only denote regular languages. So it turns out that there are many other languages which are not regular. And so by definition, regular expressions cannot denote them. Yeah. So I think we might start to see a proof of that soon. So yeah. If you have a non-regular language. Yes. Yes. It's if and only if. Yes. Nice. Yes. Good. Yes. Any, yeah. Yeah. Yeah, you can. The other question was, can you omit the dot? Yeah, because it's like kind of a waste of ink. Yeah, it's unambiguous. So yes, good question. Yes, other question? Sorry. What does the dot do? It just represents the language concatenation. So like concretely, if you have the regular expression A dot B dot A, right? Then it's there to actually represent the fact that you have A, B, A, right? So, and like the question there is, can you omit the dots? Well, yeah, because it's kind of just a waste of time, So, yes. So, all right, dots can be omitted when unambiguous. And it's actually, I think it might always be unambiguous, but don't have enough brain power to. Yeah?
So up there, we can also.
Up there?
Up there in the example where.
Yeah. Yeah, we could. Yeah, we could. Yeah, so we could also remove this and then remove this and remove this. Yeah. You'll see. Yeah. Aha, I see you haven't watched my video. I define how to concatenate two languages in my video. I'll tell you here. So to do, what does it mean to do something like L1 concat L2, right? Well, it just means that you take every single string in here and you concatenate it with every single string in here. So you do, you take X in L1 and you take Y in L2 and you do X concat Y. That's what it means. Yeah. Okay, nice. Okay, let's look at an example. So let's look at an example. So in this example, we're asking the question, what language is described by the following regular expression? So this is a bit of a boring example, apologies, but it's really just to make sure that everyone's on the same wavelength when it comes to the definition of valid regular expressions and of the languages denoted by regular expressions. Okay, so what is the language described by this regular expression, right? Well, if you wanted to compute this like sort of step by step, you would say, okay, I have to do L of R, right? So, L of R, let's replace R with what it is. So L of A B star plus B star, okay? And now by the sort of order of precedence, I see so this star has to stick with this B, this concat has to stick together, and this star has to stick with this B. So the first thing that I can do, the next step for me to sort of see what this language is I take this plus and I convert it to a union. Right? So then I get L of AB star and then L of B. Okay. And then again, order of precedence, the star has to stick to the B. So I have a concatenation here. So because the order of precedence is the star is more important, then I do the concat next. So I do LA concat L of B star. Right, so this just becomes the language concatenation. And then the L of B star, well, that becomes L of B whole star. So that becomes L of B whole star. Okay. And now at this point, I've sort of reached, so at this point, right, so what I did here was I took the star and I put it outside. So at this point, this is kind of like my base case. Now I can just start replacing, right? So L of A, that's just the language denoted by A, or L of A, that's the language that just contains A. And it's concatenated with B star, and then it's union with B star, right? Okay. And so now if we understand the language operations, then, what is this language? This is, let's expand it. This is this string, right? It's this string any number of times. So it's the empty string, b square, and so on. And it's the same thing for, I mean, it's exactly the same language operation and language, so I'll get the same thing. Okay. And with the language concatenation that I defined here, then the only thing that's left is, okay, well, I take this A and I concatenate it with each of these guys, right? So then I get A concat with epsilon, that's just A, AB, AB square, and so on. Union epsilon, B square, and so on. And so then I have the resulting language, if I represent it a bit more cleanly, is, N, ABN. So the strings that look like A and then B any number of times, as well as the strings that are any number of Bs, any number of Bs. Yeah, there's no additional quantification needed. Okay. So I know this was kind of a boring example, but it's, just to make sure that the definitions that I've just given you are like a bit more tangible. Yes. Aha. Yes, good question. So the question here is, the question was, can you do A B star plus B star is equivalent to A plus B epsilon B star? Yeah? Yeah. So the answer is yes, you can do that. And in fact, there's a whole algebra. So for the mathematicians, hopefully this is exciting. There's a whole algebra around regular expressions. And in fact, it's known as the Kleene algebra. So I won't go into more detail, but Kleene was very loud and very famous. So if you look up Kleene algebra on Wikipedia, you'll see that there's a whole bunch of rules for doing manipulations like these. So yeah, it's actually kind of, well, I'm going to go on a tangent, but I can talk to you later about why it's kind of crazy. Okay, and maybe actually, so hopefully this example, wait, actually, there was another question. Hopefully this example is clear, but I think there was another question. No? Okay. Or maybe you're just gaslighting me, but no? Okay, all right. Okay. So hopefully this example was clear. I think because I've been using this kind of operator so often, I just want to quickly give you a formal definition. I mean, I kind of did, but it's important to give it a bit more formally. So what does it mean for two regular expressions to be equivalent? So given the alphabet is not given some non-empty alphabet, and two, of course, valid regular expressions, R1 and R2. We say that R1 is equivalent to R2 if L of R1 is equal to L of R2. Right? So in general, if you want to prove something like, let's see, R1, R2 star plus R2 star is equivalent to R1 plus epsilon R2 star, then what you can do is you can go through this thing, right? And this is a definition if. So if and only if, yes. I think, I mean, since you're so interested, an exercise for you is, does this regular expression equivalence define an equivalence class? Okay, so an exercise for you. Okay, so yeah.
For such a question,
Uh-huh. Uh-huh.
when you have to do some strange in the language of
So the question was, for this particular exercise, would you have to do a double subset inclusion? I think that's the general question.
Yeah, or to prove the equivalence of two variables.
Okay, so the question is to prove the equivalence of any two regular expressions, do you have to do double subset inclusion? I mean, it depends on it's kind of hard to answer the question. It depends what the regular expressions are. If it's like something like this, then doing L of is probably good enough because we know the order of precedence for language operators. But I think the other question is, to be super formal, you might have to do induction on the length of strings here. It probably wouldn't be that intense. Just like, honestly, if I'm being honest, I guess that's why I said honestly, this is like a nice true false question. It's not like spend 30 minutes doing induction question, because who wants to do that? Okay, what time is it? 7 minutes. Okay, I want to get to like the main theorem, which I think I cannot prove in 7 minutes, but it's kind of an important theorem. So let me go through. Okay, so maybe just quickly, because you've just asked. So like at this point, what are questions we can ask? We can ask of you on, midterm, on a midterm or a final. Midterm or a final. Essentially, there's like two standard types of questions that we typically ask with regular expressions. So the first one is, given L, provide R. And like when I mean questions, I mean like long answer questions. So not true, false. So given R, provide, given L, provide R such that L of R is equal to L. Where proof of correctness are not typically asked because, like I said, the point is not for you to do induction for 30 minutes. And also, the other equivalent question that we might ask is, given R, what is L of R? Okay. So my goal is to make having the midterm seem less and less scary as the semester goes on. So hopefully this is like kind of doing that. Okay. So I want to get to the nice theorem, which I'm probably only going to have the time to state. So this theorem essentially is the spoiler that I gave just before, which is that the language or the family of regular languages is exactly the same as the family of languages denoted by regular expressions. Okay, so that's the pretty cool theorem. So given a non-empty alphabet, the family of languages denoted by regular expressions, which I'll denote L sub rex, where L sub rex is, all of the languages L of R, where R is a valid regular expression. So the reason why we spent so much time defining what a valid regular expression was is so that this family of languages was a bit better defined than if I just said, oh, it's just L of R. So the language is denoted by L sub rex is equal to L sub reg, where L sub reg is L, where L is a subset of sigma star, and L is regular. Okay, using any of the definitions of regular languages that you've seen so far. Okay. So the implication here is quite a nice one. So the implication is if, for instance, in a question, you're asked prove or show, let's make this to prove or show that L is a subset of sigma star is regular. then I mean, you can do 4 things. The first 3 are things that you kind of already knew. So you can create a DFA M such that L of M is equal to L, right? That proves that it's regular by definition. You can also create an NFA N such that L of N is equal to L. This is sort of by the theorem that you saw last lecture, that NFAs and DFAs are sort of equivalent in terms of expressiveness. And I mean, this also holds for NFA with epsilon transitions, right? So this we already knew. This is like old news, which is sometimes good news. But now a new item, so this is new. The new item here is that in addition, for us to prove that a language is regular, what we can also do is we can create a regular expression R such that the language described by R is equal to L. Again, you might, I mean, to prove this correctness, then you have to do double subset inclusion, then you have to do induction, but you probably won't ask that on a midterm. But this is kind of the new thing that we've sort of learned today. So if you don't retain anything except for one thing, then hopefully it's this. Hopefully it's not the fun fact about Stephen claiming. I mean, if you do retain that, that's cool. Okay, wait, I'm not done. I have 2 minutes. So I mean, how can I use this implication? So for instance, if I wanted to prove that any finite language is regular, then I mean, I could make a DFA. As an exercise, try to make a DFA for an arbitrary finite language. It's going to get kind of messy, but I mean, it's doable, but it's going to get kind of messy. Then you can also do it with an NFA. It's less messy, but still clunky. Or now the nice thing is I can use a regular expression, which is very nice and elegant, right? So if I have a language L that's finite, that means that it contains a finite number of strings, W1, W2, all the way to Wn. And so then the regular expression R that I can create that denotes it and proves that it's regular is what? Yeah? Yes, very good. So W1 or W2 or ... Wn, right? Because I mean, this is a pattern. This is a regular expression pattern. And it exactly describes this language because for a string to be in this language, it either has to look exactly like this or this or this, right? And vice versa, the logic is still the same. Okay, so hopefully that convinces you that this implication is nice. People are already leaving, so have a nice weekend. Yeah, thanks for coming.
I have a quick question.
Yeah. No, I don't.
You said like at the beginning, it was like it's kind of like a first of all great lecture.
Thank you. Thanks for coming.
Of course. So at the beginning, you were saying like there's essentially like it's any number of like essentially a letter, right? A or B.
Where?
Like it was like one of the first things we stated.
This one?
Yeah, exactly. So no, I think it was earlier.
Or this one probably.
Yeah. So
Any
any
number-
numbers like either A or N, right?
Or yeah, it's like so you have a string, right? Then each of these are positions in the string, and then it's like A or B, and this is like an inclusive one.
Yeah.
And then it's like A or B, and then any of them have it.
Okay, so this is like because 0 so like
Yeah, any number.
So that means yes.
Yeah, and epsilon also.
Okay, perfect.
Yeah, there's like-
Yes.
Yes.
Okay, so what I was curious about earlier. Is
Yes.
like,